Oh, hello, welcome back to this session. So in here, as is promised, we're going to be simulating Taylor series. Taylor series. So I'm just going to do Taylor series for two things. The exponential function. I know the exponential function is 1 plus x squared over 2 factorial plus just a slash x to the n over n factorial. Sorry. And maybe a sign. The Taylor series for sign. Okay. So that's sine. Sin x is x minus x to the power 3 over 3 factorial plus x to the 5 over 5 factorial, keeps on going dash to slash, x to the 2n plus 1 over 2n plus 1 factorial. Okay, let's see how those two work out and let's get our hands dirty on code. Alright, so this is the previous code on for loops and making shifts. I'm just going to make another for acquired series, .cpp. And don't forget, every file is named the CPP, so it's going to be for Euler. I'm just going to comment. I'm just going to say include IOStream using namespace std. Int men. Okay, it's IOStream, not IOStream. Yep, that goes away. So I'm going to make a few variables. I'm going to make one acquired Euler. Okay, and I'm going to make another one acquired factorial because it has to be divided by factorial. Sorry, double factorial. Make another one. And factorial is an integer, but then for purposes of division, I'm going to call it a double. Okay, to avoid integer division, I'm going to say double. Oh no, int. It's not going to be integer. Int counter. I'm using a while loop. I'm just going to say while counter. Maybe I want to go up to 7 factorial. While counter is less than 7. Okay, while counter is less than 7. Let's find Euler's number up to the 7th approximation. What that means is that I'm going to go. Let's just go back to the board. What that means is I'm going to go up to, so out of all these terms, 1 plus x squared over 2 factorial plus x to the power 3 over 3 factorial, and I'm going to go up to x to the power 7 over 7 factorial, and this is what that gives us. So I'm going to use the while loop for that. So I have to initialize factorial to 1. Euler's number also will be initialized to 1 because of this first part here, which is not part of the loop or the repetitions. This first part here. This is the one there. Okay. And then I'm going to make a variable acquired x. So double x. Then I'll ask the user what the value of x to be. So just ask it differently. Enter a value for x. Now you know what x means from the exponential. X is this thing on top here. So x is this. So if the enter x is 1, means we'll be finding for e to the 1, which is just the value for e. On my calculator, e to the 1 is about 2.71828. 1828. So since I'm going to repeat. As this suggests that it's a rational number, but we know e is not a rational number. So it keeps on going like that. And it's probably because the calculator is using some kind of approximation also. Okay, so we're going to end on 7 factorial. Let's see how that goes. Right, so I'm going to initialize counter to 1. And then factorial will be factorial is equal to factorial times counter. And then Euler's number is going to be equal to the previous Euler's number plus we didn't enter the value of x, so here I'm going to say c in x. Okay. I will probably want to include a math function also, so I'm going to say include c math to the power. Okay. So Euler's number, and then I'm going to say power, the power function, x to the power counter, and then that's been divided by a factorial. Cool. So what I'm doing is, imagine this is 1, that's going to be x to the power n over n factorial. That's what. Okay. And then after just say C out, the Euler number is Euler. And don't forget to add return 0. As you've seen from my other files, I didn't add return 0, but it worked. So return 0 is not compulsory, it's just recommended. I'm just going to say g++ series.cpp. Edit fc, enter a value for x, I'm going to enter 1. Okay, I think it's going to take a while. Oh, it has crashed, whichever was 2. Yeah, it has crashed. It didn't take so long. So I just kill the terminal. Okay, so I've killed the terminal. And if I start, let's say x is 1, so that we don't enter the value of x. Let's say it's 1. I'm just finding e to the 1. I'm just going to comment out this part, and I'm going to comment out that part. Okay, so let's see if it will give us Euler's number. I'm just going to say terminal. And g++ series the CPP, and I run that. Okay, still crashing. I think 7 factorial is a bit too big. Let me just start to 5 or 4. Again, as I said, there's a better way to do this with functions. Okay, always running the triangle function because yeah, 5, the triangle 5. Let's forget about that one. I want to compile g++ series the CPP. That compiles, and then I have edit exe. Oh, okay, an infinite loop. I'm sorry for that. I have no way of increasing counter, so I should have said counter plus plus. Okay. So the loop never stops running. And I compile that, and then run that. Okay. So I have Euler's number is 2.70835. That's according to the fifth approximation. The more I keep on increasing the approximations, the better Euler's number becomes. So let me increase the approximation to 7. So I'll go up to the 7th term. They have 2.718, which is what I got from my calculator. 2.718. Okay. Now let's say you want to have any value of x and find out e to the power any x, right? How can computer do that? So I just bring back that. I'll bring back that, and then I'll bring back power x to the power counter. Okay, I'll approximate that G plus plus raised to CPP. Run that interval for x, let's try 1. So x1 has worked. Now let's try out another one. Interval for x, I try 0.5. So you can just check on your calculator, just say e to the power 0.5. You should get what's there, which is what I'm getting on my calculator. Not so approximate. Okay, I'm getting up to 7.2, of course. Not so. I have more values than the calculator. Yeah, so because here I've ended up on the 7th term, but if I kept on going, I'd have more values also here. Let's say e squared. Okay, so you can just say what's e to the power 2 on your calculator, you get the same thing. Just proving that it's working. Cool. Let's try out for sine. Let's try out find the Taylor series for sine. So let's say Taylor dot CPP. No, let me call it sine. Sine Taylor dot CPP. I'm going to comment, so I'm just going to say this is for sine. I'm going to say include iostream using namespace std int min. If you just remember what the Taylor sine series looks like, it's this thing here. Okay, that doesn't look nice. This thing here. So you don't really care about this. You're worried about this. Let's try to simulate it. Yeah, because so I'm going to make a variable. I'm going to create int counter. I'm going to have another factorial, so I'm just going to create double factorial. Now again, the factorial is really an integer, but then for this purpose, I'm going to make it a double. Initialize it 1, and then I have double x. Cool. So I'm going to have x degrees and x radians. That looks nice. We ask the user to see out, enter the angle. This program finds the sine. And they'll enter the angle in degrees. We have to convert it to radians. So x radians, I hope you all know how to convert. X radians is equal to, okay, I'm going to include CMAT, so I can use the pi. Include CMAT. I'm going to make another variable called pi. Double pi. Now pi is arctan. Sorry, arctan of 1 times 2. So 2 times that. Let's try to out print out of pi. Let me try to print out pi. Okay, I want to run that code. Run that code. So G++ sine Taylor.cpp. Then I'm just going to run it, edit.exe. Okay, so it's printing out 1.57 that I have to multiply that by 4. Explain what I'm doing here. I'm just trying to find a value for pi. Okay, that's pi 3.1457. Now we know what arctan is. So I know that tan of pi over 4, 45 degrees is 1. So if we say arctan of 1, I should get pi over 4. But then to get a value for pi, I have to multiply this by 4. So meaning pi is just equal to arctan of 1 times 4. Okay. If you can still say arc sine of 1 times 2, because arc sine of 1, sine of pi over 2 is 1. So if you want to use sine, you have to multiply it by 2. Okay, that's one way you can get value for pi using the same math function. You just have to know how everything works. So let's say I want to use sine. So say 2 times arc sine. So arc is a sine. Of course, you have to include CMath library to use that. Just compile that and run it. So I get the same value for pi. Cool. Whichever one works with you. So let's enter the angle in degrees. Now, why is this stress pi? Because I want to convert from degrees to radians. So x radians is going to be equal to x degrees. I'll multiply that by pi. Then I'll divide that by 180. Okay, cool. That will be x radians. So you can print out x radians if you want to, of course. But then after you have decimal points, because I'm multiplying by pi, so then you leave it there. And then let's use the loop, a while loop. So I'll say let's go up to 7. So while counter is less than 7. Then I'll say factorial is equal to factorial times counter. This time let's not forget to add 1 to counter. So counter plus plus. Cool. We're almost there. Now for the hard part, finding the sign. I'm going to make a variable create the sign. So I'll say double sign value. I initialize it equal to 0. And here I'll say the sign value is equal to, okay, so the sign value is equal to what you entered in radians, x radians. Okay, there goes. Sorry, the previous sign value. Don't forget to add the previous sign value because you keep on adding. And then you're multiplying by -1. So use the power function. Power -1 to the power n plus 1. Now n in this case is a counter, so counter plus 1. And then to this I'm multiplying, again I'm multiplying power x to the power 2n plus 1. So that's a bit 2 counter. -1 rather, sorry. -1. Okay, we're almost there. X radians. X radians. We're almost there. I just have to make a small check. Okay, a small check. Because the check we're making is now when dividing by factorial. This is almost working, but then it's still going to work on it. And dividing by factorial. Which factorial do you have to divide in? Again, this is where that comes in real handy because I'll just say it's 2 counter. Functions come in handy. I can just say 2 counter. 2 times counter -1, then I just say factorial. But then I'm not using that here. That's not going to work. I have to make a function called factorial. Let me figure out a way to just pick out the odd numbered factorials for that n. Okay, there goes. Let's print out the factorial. See out factorial. If it's odd numbered, so I can say if factorial. No. If counter is an odd number. That's one way I can do it. Okay, if counter is an odd number, so I'll use moduli. Divide by 2, it leaves the remainder of 0. It leaves the remainder of 1. It leaves the remainder of 1. Then that's why it's an odd number. Okay, and that's going to work. We'll just check because this is only going to work for odd numbers. and then you put it here. That so I have to divide by factor only if it's an odd number. Okay. Let me just print out the factor itself. So just say C out. I'll print out the factor. Okay, let me print it out from here. Again, let's print it out both ways. And I'll just leave a space and here a blank space also. So blank space, blank space. Let's go and see how that goes. Into the angle. I'll say 30. Oh, okay, that didn't work. This thing I want to work on. Oh, into the angle. Come on. Not working. What counter is this one? 7? Oh, I have to initialize the counter to 1. Cool. I didn't give it an initial value. THGBs. So there goes. I'm printing out. So 30. I don't have a number which is 11 factor. Factor starts with 1. Sign value. 266. I don't know what this is. Let's try that again. Okay, time for some debugging. Let me leave a space here so I don't know what comes from where, what's coming from where. Enter 30. So there goes, it's printed out 1, 1, then 2. Okay, so it's considering 2 to be an odd number. Then 6, 24, 127, 20. Okay, sure. Just to be safe, I'll say the even. Here let's also check and counter is not equal to. Cool. That's saying the odd factor is enter 30. So the factor is 1, the odd factor is 1, factor is 2, so it's working. Sharp, so it's working. For even numbered factor, for odd numbers factor, so that's the first one of testing if I remove that nonsense there. So now I only have odd numbers factor, and that makes it certain that I know what I'm doing there. I'm only dividing by odd number factors. So when all this is done, I'll have a value for sign. So here I just say out the sign of what you entered. x degrees is, sorry, sine value. Don't forget to add return 0. G plus plus sine Taylor.cpp a.txt. Okay, I'm going to enter 30. So there goes the sine of 30 is 0.5659 because it's only performed one iteration. I'd have loved it to perform more. Okay, so odd factor is 1. It's only given me for 1. It hasn't given me for 3. And it hasn't given me for 5. Okay, so it's only given for 1. Try that again. So 30. Okay. Factorial equal to factorial times counter. That's more correct. G plus plus sine Taylor.cpp. Into 30 degrees. Yeah, we're getting there. 0.53. The more terms I use, the better it becomes. So let's try to go up to 9. Okay. Although we may have an overflow. So after 9. Again, it's better to use a function. A function will work better than this. So say 30 degrees goes 0.53. Well, we know the sine of 30 is 0.5, but then we're just using an approximation to 0.53 somewhere there. Of course, with a few errors here and there, but that's how you do it, and that's how you find Taylor series with sine and cosine. You can get a little better when you do functions, but for now, I guess we'll work with this.